All right. Lagrange error bound, or as he probably pronounced his name, Lagrange. Joseph Louis Lagrange. It's French. Yeah, it's kind of like Lagrange. Yeah, that one. It's a good song. But we've seen Joseph Louis Lagrange earlier in this year. Do you remember where he showed up before? He built on the work of Michel Rollet, or Roll, or however you say his name. Rolle's theorem. Remember Rolle's theorem? If the function is continuous on the closed and differential on the open, and the derivative equals 0, then there's guaranteed to be an x value where the horizontal tangent occurs. Oh yeah. Okay. But he said that the derivative had to be 0, and then Joseph Louis Lagrange came in and cleared up that hurdle, because that doesn't always happen. So he said, hey, if the derivative isn't always 0, the derivative will always equal something. If it's not 0, what is it? MVT. I'll just give it away. MVT, right? Joseph Louis Lagrange did the MVT. So as long as it's continuous on the closed, differential in the open, then there's going to be a place where the derivative is not necessarily 0, but it'll also always equal the average rate of change, right? The derivative equals the difference quotient. The slope of the tangent line equals the slope of the secant line. So he's back. Here he is. He's back. Little French guy. Back. All right. Now, let's take a look at this. There's other names that you might have for this. Lagrange form of the remainder. Sometimes it's just called Taylor's theorem, because Taylor kind of built the most important part of 9.2 through 9.5, which was this. Let's just review. This is the most important kernel from this section. It's the fact that you can generate polynomials to approximate, if not totally equal for infinite eliminate terms, transcendental functions like sine, cosine, and e. That's the most important thing, right? This is the coefficient of that term, and this, of course, is the variable part of the term, and c is equal to the center of the approximation. And if the center is 0, we get Maclaurin, okay? So what Lagrange did is he took this idea, and like we did with the alternating series remainder and the integral remainder, we did that too. He said, hey, there's a way that if you're approximating something with a Taylor polynomial, there's a way to figure out, how close that partial sum or approximation is to the actual. We're not going to be able to find the actual error, because if we were, then we'd know what the actual value is. We're still approximating it. But we can establish an upper bound. We know that the error is not going to be greater than this. So it gives us an interval in which it lives. Now, the upper bound on the error is very important to be as small as possible, because there goes my drums. Okay. If you just say, hey, I approximated something using a polynomial, and someone says, well, how accurate is it? I mean, is it a good approximation? How close is it to the actual thing? And you're like, I don't know. It's within like 42 trillion units of the actual value, right? 42 trillion. That's a pretty safe upper bound, but guess what? That's a meaningless upper bound, because you're like, you might as well not have done anything, right? So we want our error bound, or our remainder, as it's also called, to be as small as possible. But it has to be big enough to be sure that, the true value lies on the inside of it, not on the outside of it. Does that make sense? So it is an upper bound. Now, there's a lot of different ways we can write errors. Let's just kind of come off to the side here. I'm going to add a page, actually. Add a page. There we go. Let's say that I have a polynomial of degree n, and it's used to approximate a function, okay? So I know that f of x, whatever the function is, it can be approximated by a polynomial of degree n, right? We've already done that. That was 9.2. We might want to find out what the approximation is at a specific value. So let's just say here's where we get in the trouble. We have so many different variables. Let x equal, I'm going to call it a. All right, where a is just some random number, right? I want to know what the function value is at a. Well, I'm going to approximate it with the polynomial, because I don't know how to evaluate the function, or I may not even know what the function is entirely, but I know I can generate a polynomial for it. And if I go out far enough, the approximation is going to be pretty good, but it's only going to be the same at the center. After that, it's just an approximation. So here's what we could say. We could say let x equal a, and then we could say this, right? We could say that f of a can be approximated by p sub n of a. This would be the actual value, which is unknown to us. We don't know what it is. That's what we're trying to find. And this would be the approximated value, right? Which is only an approximation. We do know this. We can find this. This is known. Okay. So here's what it might show up. These are all going to be the same. These all mean the same. Let's kind of create a little list down here. If I take the actual value, f of a, and I subtract the approximated value at a, that difference will be the error, right? Would y'all agree with that? Now, it doesn't really matter. If I do f of a minus the polynomial approximation, then I know if that number is positive, then I know that the actual value is bigger than my approximated value. So my approximation is too small. But if I do f of a, the actual, which I don't really know, minus this, and that number is negative, now I know f of a is smaller than that. And then I know that my approximation was too big, right? So the sign of the error can be important. It can tell you on which side of the true value you live. But if you've taken statistics, you know something like margin of error. We typically take the absolute value of it because we really don't care about the order. We don't care if we're too big or too small because we're just always going to take it as an upper bound. We're just going to use that as an upper bound. Worst case scenario, if you will. So you might see it like this, or it might be flipped around. You might have the approximated value minus the actual value and the absolute value. And that's all this is. If you want to write this down, this is just the approximated value minus the actual value. That's all it is. It's not a percent error. We're not dividing it by anything. It's just the error. It's the amount by which we are off, okay? This is also called the error, which makes sense. I think in science class, y'all call that error. But it's also called the remainder, okay? Which makes sense as well because we're not dividing here like a remainder, but it's what's left over when we do that difference. That's how much we're off by. Now, we can't really find that number. We can't find the actual error. Can't. So there are certain ways, though, again, that we can set an upper limit on what the error is. With the alternating series, remember, if we use, let's say, 5 terms for our partial sum as the approximation, the alternating series says, hey, the remainder, the error, this difference is going to be within the absolute value of the first unused term, right? And then because it's an alternating series and we can add or subtract, we would then use that number to add to our partial sum to get an upper bound, and then subtract it to get a lower bound. And that gives us an interval in which it lives, okay? If you have just positive terms, then all you need to do is use your partial sum as the lower bound, because it's not going to get smaller. And then you use the upper bound plus the error bound to get the maximum. And then you get another interval, okay? So whether you're calling it this, that, or that, the other, oh, this, by the way, this is the same thing. R sub n of a. Let me write that in there. We can actually write the remainder as a function of n, okay? So if I did the sum of the first 5 terms, S sub 5 would be the partial sum, and then R sub 5 at that value would be the remainder for using a 5-term sum, okay? Now, what we can do is we can find a way to say that all of these are less than or equal to some number. What do you want to call that number? Maybe capital E for error. Don't get it confused with energy, right? Or, yeah, some number. This then is what we would call the error bound. Okay, it's not the error, it's the error bound. It's the maximum error. It's the I'm going to say it's the smallest maximum error. That's kind of a oxymoron, right? It's the smallest maximum error. We don't want to just every time say, yeah, we're going to be within like infinity. I just did a real guess. How fast are you driving to school today? I don't know, probably like 42 million miles per hour, you know, give or take infinity, right? Like, okay, well, you're right. Your true speed fell in that interval. But, you know, first of all, you need to drive less than that, not that fast. Right? You need to drive kind of like Hank does, going over speed bumps in that sports car, right? Nice and safely, slowly and safely. Okay. All right. So this is the idea of an error bound. When we did the integral test, you didn't have to know the integral error, but the integral test said, hey, if you add up the first 7 terms, then the error, that is going to be within whatever the integral from 7 to infinity is on that improper integral. That gives you an upper bound, okay? You didn't have to do that. The alternating series says it's the first unused term. What this gives us today is a way to find that number when the integral test doesn't apply or when the alternating series test doesn't apply. It gives us a way to find the maximum error or the error bound for any polynomial approximation, whether it's linear, quadratic, cubic, quartic, whatever. It gives us a way to find the maximum error. So that's the idea that this part contains, right? The idea itself is pretty easy to understand. But for some reason, students just love to hate Lagrange error bound. He gets a bad rap for some reason. I don't know if it's because it's the last thing and the students are kind of fatigued, or they hate Lagrange. I don't know. Like, I didn't even know the guy, right? But let's go ahead and take a look then. Now that we have the idea planted in our head, if we don't have a calculator, but we're interested in approximating, let's say, the value of sine of 1 radian, the sine of 1 radian, right? It was like 57 degrees. And we don't have a calculator, but we were interested. How would we approximate its value? Would we eyeball it on the graph? Is that one way to approximate it? Here's Sahala, right? Here's pi halves. So 1 would be right around there. So I know the maximum is 1. So it's going to be, I don't know. I'm going to call it 1.8. What do you think? What do you think? Is that good? I'm just using the old eyeball test, right? All right, what's sine of 1? It's about 1.8, right? Give or take, I don't know, give or take 12, you know? Right. Now what could I do as a reasonable give or take? Give or take what? Let's say I have the wrong graph, but I know it oscillates between 1 and -1. How far would it be from -1 if it was closer to -1 up to 1.8? What would be that distance? 1 unit plus another 1.8? Actually, that's not 1.8, right? I'm yes, 0.8. That's yeah. You know, I didn't pay attention to math class, you know. Boom. Yeah, good. Boom. Hey, how about 0.8? Is that better? Do I impress you now? 0.8. Yeah, 1.8. This sine ratio 1.8. Yeah, the hypotenuse ain't the longest side in the right triangle. Yeah, go figure. No, that doesn't work. Forget about it. Forget about it. So I could say now, truthfully, with the eyeball method, for seriously, I was thinking more of jokes than math. That's bad. I need to frame my brain. Give or take what? Sine of 1 is 0.8, give or take 2, right? Give or take 2. That would be safe. Because if it was actually closer to 1, like 0.999, but I have my graph wrong, maybe it's closer to -1 actually, right? So how far would it be from -1 up to maybe 1? That's 2 units, right? So if I put my margin of error as 2, that would be a safe thing to say, right? I know for sure. Could I say it's less than 2? I probably can, because I know that at 1, it's not going to be at the high point, but I don't know where it's at. So I can't with any confidence say less than 2. I can't, right? But 2 has it covered. Now, if I say give or take 12, would that also work? Yeah, but that's a meaningless thing. So that's the idea behind error bound. We want to make sure it's as small as possible so it's meaningless, but we got to make sure that we're capturing the true interval in which it lives. All right. You could compare it to sine of pi thirds, which is kind of what I did the pi halves, which is 1.5. But pi thirds is actually closer to 1, isn't it? Because pi is 3.14. So if you knew what the decimal approximation of square root of 3 halves is, I think it's like 0.8 something. So would sine of pi thirds be smaller or bigger than that? Pi thirds is to the right of 1, isn't it? It should be a little bit smaller. So if I know the square root of 3 halves is like 0.86 something, I don't know what it is. I can say, yeah, maybe it's like 0.85. I'm just 0.85, give or take 2, right? Plus or minus 2. I got it covered. You could do a tangent line approximation. Where would you center your approximation? if you wanted to calculate sine of 1 and you wanted to do just a tangent line approximation, where would you center it? Would you center it at 1? There's no way you want to center it at 1 because you don't know what the y value at 1 is. That's the purpose. But could you center it at 0 and make a tangent line? And you can see right here by this, it would work. It would be an over approximation, but you know, some people won't be happy with that. Could you center it at 0? Or I mean, pi halves, could you center the tangent line at pi halves? You certainly could. But what type of tangent line do we have there? No slope, right? So you would say, it's about 1, right? It's about 1. You know, I know it's less than 1 because it's concave down, but it's about 1. Or here you would say it's about whatever, what would it be? It's about 1. This would also be 1 because it's a 45-degree line. So you could do that. What other method do we have for approximating sine of 1? Euler's method is another method for approximation. And what Euler does is like, you know, you Taylor guys, you like your higher degree polynomials, but you know what? I like lines. They're easy, right? I can plug and chug with lines all day long. So Euler came up with a method that said, hey, let's just break it up from 0 to 1, and we'll just walk out on tangent lines. It's like reevaluating every time. And the more times you do it, we're kind of hugging the curve, right? Like when Hank's going around the plaza and he's like, I better stay on the road, right? He's hugging the curve. He's recalculating. He's pulling the steer. He's hugging the curve. But you don't want, you don't want to lose control, right?
He starts to fishtail a little bit.
That's Euler's method. That's Euler's method. And then, of course, what we learned in 9.2 is we can use a Taylor polynomial of a degree bigger than 1, right? And as we do that, that accomplishes the same thing Euler's method does. The more terms we use, the more it becomes the curve. And we said for sine, if you use infinitely many terms, it's no longer an approximation, is it? It's a identity. It's actually the same. Physically impossible, though, to use infinitely many terms, but in theory, totally possible. So we would say that one converges. So we talked about that. Now, we talked about the remainder, so I think we can skip all that, but that's kind of what this is saying. I just use different values there, okay? When I say function here, think of this as the actual value. The actual value should be your approximated value plus the remainder. Thing is, we don't know what the remainder is. If you solve it for the remainder, you get function minus polynomial approximation, and that's what we already talked about, okay? And we take the absolute value of it. So I kind of reformatted this explanation when we did this right here, okay? And I think maybe y'all understand that. So maybe I'll update my notes for next year. Now, here is the remainder, and don't be scared by it, okay? We have a center at C. Oop, I mean, don't put C equals C. That's so profound. We have a center at C, and we're evaluating at A. Let's put X equals center at X equals C, and evaluating at X equals A, okay? So for instance, what we just did with sine of 1, I would probably center my approximation at 0, because I know sine of 0 is 0. And then my A value would be 1. I want to evaluate it at 1, okay? So that's what those two letters mean. So here it is now stated. The remainder, when you use n terms or an nth degree polynomial to approximate f of A at A, it's equal to T. I use T for the Taylor polynomial, but it's your approximated value minus the actual value, and we take the absolute values of it. Now, here's where it gets fun. Here's Lagrange error bound. We can actually, and this should not be an equal sign there. I need to change that as well. So help me out with this. This should not be an equal sign. I'm going to go to a white marker. That should not be an equal sign. That is where the magic happens. I got a little careless. Bless you. Less than or equal to. Less than or equal to. This right here is the Lagrange error bound. The Lagrange error bound. The error will not be bigger than that value. And notice it's an absolute value. Do you notice a pattern in there? Is there a familiar pattern? Yeah, we have f of parentheses n plus 1. That means derivative, right? So this would be the n plus 1 derivative at z.
Don't let z scare you.
Don't let z scare you. Don't let z scare you. It's just some x value. I'll talk about that in a second. It's the n plus first derivative divided by n plus 1 factorial. Hey, That piece right there is nothing more than Taylor's rule for generating coefficients, isn't it? But notice, like the alternating series, if I'm using n equals 5 terms, let's say, it's going to be less than or equal to the 6th derivative over 6 factorial. So like the alternating series, it's less than the absolute value of the next one, right? The next one that's unused. So it's still in that spirit, but there's a little more to it. We can't just take that term. It's we'll talk about that in a second. Now look at this part here. Instead of x minus c to the n plus 1, we actually plug in for x. We plug in the value of a minus the actual value of the center to the n plus 1 power. So those match up. N plus 1 derivative over n plus 1 factorial to the n plus 1 power. The only thing is this thing is a number. This is a number. It's not a variable. It's a number. And it is the upper bound. The upper bound, you could say, on the error, which is also called the error bound. Now let's talk about this part right here, because this is the part that leaves people kind of dissatisfied, confused, whatever. What the heck is z? Well, z is defined to be the x value. Maybe I define it down here. Did I write it? Where's z? Okay, let me write it up here, just so you're not confused. We'll just keep going with interpreting this a different way. But what is z? Okay, and in today's day and age, when I write that, it kind of, it reminds me a little bit of. Oh, I was going to say it reminds me of. Yeah, the Ukraine, right? The Russia, right? They've kind of taken z away from people, right? Yeah, I mean, that's a letter. We need z. We need z, right? Yeah, so I always put the line through it like that because my twos look bad. But anyway, what is z? Z is the x value on the interval from x equals a to x equals c. Okay, so you can write it like this. That would be x on the interval from a to c, or it could be x on the interval from c to a. We can evaluate at a, and a can be to the left of the center or to the right of the center. Typically, we evaluate to the right. But we've done some Euler's method where we go backwards, don't we? So we don't know if a is bigger than c or c is bigger than a. So when we write it as an interval, we're just going to say, hey, z is the value that's on the interval between a and c. A is like the 1 in the sign of 1, and c is the center like 0. Somewhere on that, I guess we should put, let's put brackets there actually, because it could be an endpoint. It's like an EVT now. Z is the x value on the interval from x equals a to c that, or I should say where, let's do where because it's a location, where the f of n plus 1, that's the n plus first derivative, is maximized. We want to find essentially the maximum value of the first unused derivative on the interval from the a value that I'm trying to approximate and the c value of the center. Somewhere on there, if I can see what the next derivative graph looks like on that interval, I can maybe find that upper bound. Like when I just drew the graph of sine at 0.8, I could see the bottom was at -1. So if I say I'm off by a maximum of 2, I know I've got it covered. Okay, that's the safest upper bound that we can come up with. That's why we have the maximization here. We're trying to find the smallest but safest value of the n plus first derivative on the interval between a and c. That's all it is. And if I know that value, then all I have to do is come back in and plug it in right here. And then I can compute that number, okay? So you don't even ever have to find a z. You don't need x equals z itself. You need the max of the n plus first derivative, okay? I'll say this again, on the interval from a to c or c to a. You never have to find z. Now, how are we going to find the maximum value of the first unused derivative? That's what this all comes down to. Well, there's different ways we can accumulate it. We can kind of come across it like at a rummage sale or something, like, oh, look, this person's getting rid of this maximum value of the first unused derivative. But one man's trash is another person's treasure. It's unused no more. I'll use it. No, you could actually be given it. It could state in the question, and you're reading it like, it'll say something like f parentheses 6 has a maximum value on the interval from 3 to 5 of 7. And you're like, good to know. And then you're working down later and you're like, man, I need to know what the maximum value is for the what derivative? Fifth derivative from, what did I say? I forgot what okay, the sixth derivative from 3 to 7. I forgot what I said. But I need that value. And you're like, where do I go get it? And you're like, oh, it's up there. They gave it to me. I was wondering when I read it why that was there, but now it makes perfect sense. So you could do that. That's the easiest way. Or you could actually be given the function, the equation, and you yourself could compute that next derivative, and it should be a recognizable function. If it's a non-calculator question, it would be one of your parent functions. And then you can just draw a picture of that graph on that interval like I did for sine of x here. And you can be like, oh, yeah, the maximum value on that interval is the right endpoint, the y value at the right endpoint. Or maybe it's the y value at the left endpoint. Or maybe there's a local max in the interior, and that local maximum, which is the absolute maximum on the interval, is the y value I want. Okay, so that's another way to get it. What they've been doing in recent years is they have been giving you a graph of some nth derivative or n plus first derivative, and they give it to you on a wider interval than between A and C. And now you have to look at the graph they give you strictly on the interval from A to C and find the maximum y value. Okay, those are pretty much the three ways we find that value. It's given to you, we compute it ourselves, or we get it from a graph. Okay, but once we have it, it's just plug and chug, baby. Plug and chug. And do we have to remember really anything else to make that happen? Not if we know Taylor's form for generating coefficients and terms, because it's the same form. It's just the next unused term. And instead of having x minus with x in there, we're actually plugging in for x. So that's an actual number. Okay, now the cool part about this is if you know this, you really don't need the alternating series error anymore, because this kind of has it covered. Like we don't need Rolle's theorem anymore because we have the MVT. Man, Lagrange just puts people out of business, doesn't he? Yeah. Wow. We don't need Rolle anymore. We don't need alternating series error. Lagrange has it covered. But the alternating series error still works. And I've seen questions like this on free responses where it is an alternating series and it uses a polynomial approximation and it says to find an error bound. And you're free to just say, oh, it's the absolute value of the first unused term. But you could also do this, okay? So let's go ahead and work a problem. Oh, here he is, look. I did that in Microsoft Paint. Are you proud? Microsoft Paint, that's my photo editor of choice. I love it. It's easy to operate. Yeah. On my Windows Vista operating system. I'm a Windows 95. Windows 95, yeah. Yeah, the Rolling Stones got rich off that. Absolutely, yeah. Start me up. Have you seen the video of all of them dancing on stage awkwardly? Start me up, come on and start me up. All right, anyway, they're millionaires, billionaires now. But anyway, oh yeah, I think so. So this is Lagrange, and then this is him going to a ZZ Top concert to sing Lagrange with ZZ Top. Did he really have that beard? I know it kind of looks like it's part of the photograph, but yeah, he wishes. He did kind of have a pointy little nose. All right, so let's go ahead and try one out. Let's try one out. Example 1, calculator permitted. Okay, we'll see if we need it. Let f be a function with 5 derivatives on the closed interval from 2 to 3. Got it. And assume that, here it is, assume that the absolute value of the 5th derivative at any value of x is less than 0.3. That could be less than or equal to. For all x in the interval from 2 to 3. So, well, what is that? Why are they telling me that? The maximum value, that's your f of z, right? 0.3. This derivative never gets bigger than 0.3 on that interval. Okay, good to know. I don't know where I'm going to use it, but I'll just remember that. We also know that the 4th degree Taylor polynomial t sub 4 of x for all f at the centered at 2 is centered at 2. It's your c value, is used to approximate the function at 3. So 3 is your A value in this case, right? 3 is the value we're interested in, but we're centering it at 2. So we're going out 1 unit on a projection here, okay? That's good to know. I don't know what the function is, right? I don't know what it is, but they're telling me some information about it. That could be good enough. Part A, how accurate is this approximation? Give 4 decimal places. It's within 5,000,000,000 of the actual, right? Hi, Coach Fair. Yeah, how accurate? That you get +0 for that.
Coach Fair, how are you?
Boy, howdy, he's dandy. Bye, Coach Fair. Okay. This question doesn't say anything on part A about find the error bound. It doesn't say use Lagrange error bound. Sometimes it does. It'll say using Lagrange's error bound, and you're like, oh, I hate that, right? This is how accurate. So you got to kind of figure it out for yourself. Well, I don't know, but maybe if I can get an, maybe if I can if I can figure out what the approximation is using the further degree polynomial, and then I can figure out what the error bound is, I know that the approximation will be within that amount of the actual number. Boom. Okay. So that's how you think error bound. Now, what are we going to do to make it happen? Because notation is everything, right? They're telling you this right here. So if you want to say something like the error or the remainder, if you want to call it that, it's going to be the absolute value of the Taylor polynomial with 4 degrees evaluated at what's our x value? C equals 2. And yeah, I'm going to put A equals 3. I'm going to call it A. So this will be 3, right? Minus the actual function value at 3. That's the actual error, right? And does it matter that I put the Taylor polynomial first in front of F? No, because we're taking the absolute value. So that really doesn't matter. Now, the notation that we give for that typically is this. We call this the remainder R with the subscript of what? It has the same subscript. Good. You don't use the subscript for n+1. You use the same subscript for the polynomial. So we're saying, okay, when you use 4 terms, here's the remainder or the error for the 4 terms. And we're evaluating it where? We're evaluating it at 3. C is just your linchpin. We're going to start there and go from there. That's our starting point. We're interested in 3, okay? So that would be the notation. Now, here's what we're going to write. That is less than or equal to. This is where the error bound comes in. The absolute value of, let's see, what integer comes directly after 4? 5. So that's going to be within the 5th derivative of z, and we know what that means, all over 5 factorial times x minus c to the 5th. Okay, x minus c to the 5th. So does it matter if it's 2 minus 3 or 3 minus 2? It doesn't, because we're going to take the absolute value of it anyway. Yeah. So I just like to do a big minus small. So I'm going to do 3 minus 2. But you don't put an x in there, right? You put the actual value of x, which we're calling a, and then c is the center. Now that's not quite a number, is it? Yeah.
If the interval is more than like one number, wouldn't it matter? Because then the number that you're multiplying isn't going to necessarily be a 1, you know?
Wait, one more time.
Like this interval, 3 minus 2,
Uh-huh.
it's either going to be negative or positive 1.
Right.
What if the interval was bigger than that? Then wouldn't the order matter then?
Well, yeah, the magnitude would be the same. The magnitude would be the same. A negative number to the 5th would be a negative number, but the magnitude would be the same. But so because we're taking the absolute values, it doesn't matter. Okay, as long as we take the absolute values. In other words, like negative 2 to the 8th power is, or sorry, that's that part. How about negative 2 to the 5th power? Negative 2 to the 5th power is negative 32. But now I take the absolute value of negative 32 and I get positive 32. Maybe I don't understand the question.
What if the interval was like 3 to 7?
Oh, okay. From 3 to 7? Yeah. Yes, correct. Yes, 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 yes.
What about if one of them was negative? So then if you.
Oh, then you would treat it as a negative number minus the other number. Yeah. Or the number minus the negative, which would make it plus. Yeah. So you can have negative numbers. You just always subtract them.
Okay.
The order doesn't matter. A minus B or B minus A. Negative minus a positive or a positive minus a negative. Okay. Does that make sense? Now, here's what's cool. Yeah, they're going to give you the interval 2 to 3. These are contrived problems. They're going to actually kind of work out nicely for you. In the real world, if you're encountering something like this, you don't really have the luxuries of a prefabricated problem. So what we're going to do now is we're going to substitute in. By the way, College Board, I think they don't even put the fifth derivative of z. They actually do something like this. They write the word max of the fifth derivative of x. I don't like that notation. I don't like that notation. I really, really don't. Yeah. It's like slang. But I'm not going to take issue with College Board. What? It's the same thing as the fifth derivative of z.
Like would the whole numerator be 0.3 or would
Yes, the whole numerator would be 0.3. Yeah. Yeah.
So you wouldn't just plug in 0.3 for x there.
No, you would just, that whole thing becomes 0.3. Okay. Yeah. So anyway, keep that in mind. It'll say max of the derivative, and that's them trying to help you out. That's like giving you a crutch. Yes.
Maybe jumping ahead. Sometimes are they going to be like z, but not like the fifth derivative of x, so then you have to find
like plug in.
The graph or something.
Right. Yeah. We'll work one like that where we're kind of like squirrely and iffy. But whether it says the maximum of the fifth derivative, or for me, a purist would be the fifth derivative at z, and then you would define z off to the side. What is z? I like that better. But we are trying to maximize that. So now you're like, oh, look. This says that the absolute value of the fifth derivative is always less than 0.3. So 0.3 is the maximum value for all x, okay, in the interval from 2 to 3, which happens to be my a and c. So when we substitute it in, and this is our toe getting wet in the water, now, let me see if I can scoot that over. No, I'm out of room. So what I would do now is when I work straight down, I would like to go out to the right one more time because I want to put an equal sign there, but I don't have enough room. Maybe can I scoot it over, remodel? Let's remodel. Okay, there we go, remodel. There we go, boom. Error's kind of off the screen, but that's okay. So you only use the inequality once. That's when you go from the notation, whether you write it as error or you do it as a subtraction of absolute values, you put the inequality one time and then it stays. And then after that, you're working with equals on the right side. So this becomes 0.3 over 5 factorial times 3 minus 2, which is 1 to the fifth. And then that would be a numeric answer. Okay. Now, sometimes they might have, like on a multiple choice, an answer that is not quite like this. So you can simplify this, right? If we come down here where there's room, let's work on that a little bit. I could drop the absolute values right now because everything's positive. So 0.3, that's the same as 3/10. And times 1, I don't really need. So now it's times 1 over 5 factorial, which is 5 times 4 times 3 times 2 times 1. So you might actually have to do this. They might say, show that the maximum error bound is a number. And now you have to compute it out, even on a free response, to show it's like a proof, right? And now what can we do when we expand it out? Well, I can divide out the 3's. So that makes it 1 over, oh, hi, Jensen. Yeah. So what are we left with here? We're left with 5 times 4 is 20. 20 times 2 is 40. And then 40 times 10 is what? 400. So there you go. They might say in a free response, show that the polynomial approximation is within 1/400th. And if they say that, that's where you actually have to show the computations. You don't just like come up here and in place of this put 1 over 400 because you're not going to get credit because that's just using their answer. You have to show the technique and the arithmetic. But this was a calculator question. So if it's a calculator question, you can go ahead and type it in. Okay. I'm not going to type it into the calculator because I think everyone knows how to type it into the calculator. You can use the factorial button, right? It's 5. It's math probability 4. But it might be on a non-calculated question, and you might have to simplify because they show, right? So that wasn't that bad, right? That wasn't that bad. That wasn't that bad at all. Okay, yeah. No questions? Okay, good. No, none. All right, awesome. That was Lagrange error bound. Y'all are still here. You're crying a little bit. Is that because you yawned? Not because it's hard?
Well, no, I'm gonna be crying.
Oh, okay. No pain, no gain, baby. All right. So let's go to part B. Suppose that the polynomial approximation at 3 is 1.763. 1.763. Use your answer from part A to find an interval in which f of 3 must reside. F of 3 must reside. Now, look at f. Does it say anything about whether f is an alternating series or not? Do we have any indication that this is an alternating series or that all the terms are positive? Does it say that all the terms are positive? No. So if I am going to actually truly find an interval, would I take my approximation and add and subtract the error bound to get the interval, or should I just use my approximation as the lower bound and then add the error to the upper bound? What would be the safer bet? Add and subtract. Yeah. If it's an alternating series, you better subtract, because now the next term might make it smaller. And I'm not just going to assume that all the terms are positive, and I'm not going to assume that it's not an alternating series. It doesn't give us any indication. So to be safe, we'll add and subtract. So here we go. We'll say this. We'll say the actual value f of 3, f of 3, must live in the following closed interval. It'll be the approximation minus the remainder. And you don't have to write this notation. I'm doing this for y'all's learning benefit. That's the lower bound. And then the upper bound will be the approximation plus the remainder. Close bracket, okay? We do want to put a bracket because it could be the maximum, right? Now, would you get credit for that right there? For the final answer? No, but you might get credit for a notation. You're clearly indicating what you're going to do here. And then you could say over here that this is going to equal, we'll put an equal sign now. This interval is actually now equal to 1.763 minus 1 over 400. And then 1.763 plus 1 over 400. Now, if this were a calculator permitted question, could I leave my answer like that? Or are they expecting me to give that as a single decimal? It's a free response. Is that a numeric answer? It is, yeah. So just because it's a calculator question doesn't mean you need to pick it up and give it as a decimal answer. You can leave it like this. That's exactly right. Exactly right. Exactly right. Right. So anyway, I would leave it like that. Okay. It's not very satisfying, right? But it's enough. It's good. Now look at part C. I was just going to say, we might have to just cross a bridge, but we're not going to cross it until what? Until we get there. Have you ever tried crossing a bridge and you're not there yet? It feels awkward taking that step onto the bridge to cross it, and the bridge is way over there. You're like, what am I doing? There is not even a bridge here. I do. So I'm going to leave it like that until I need to have it in a different form. Part C. Could the function live? I mean, could f of 3 actually be 1.768? Will high or will high not? Well, dang it. I need to know if 1.768 lives in this interval up here, right? And I got to compare apples to apples, right? And I got a pair in there. So, right? Let's go ahead and see. Now is when I would type it in. Nice. I see what you're doing there, Bendelay. Yeah, I see what you're doing there. You and Kesha would get along great. You don't know who Kesha is? She sings a song about what you were just talking about. She sings a song called Grow a Pair. Have you not heard it?
No.
Oh, am I more tuned into pop culture than you?
Probably.
Oh. Yeah, okay.
I thought it was pronounced
Keisha. Right. That's only at breakfast when she's eating eggs.
Yeah, I've seen her name before.
All right, so here we go. Oh, I lost it. I'm recording. Why am I? This is not quite. Are y'all done already? you're done already, right? Does anyone have it? You want to just call it out to me? Okay, yeah, thank you. Let me get rid of this. Just hang on. Sorry, calculator, maybe some other day. All right, so here's what I'm going to say. On part C, I'm not on part B, but on part C, I'm going to write it out. So who's got it? Who's the lower bound? Okay, and the upper bound? 5.5. Okay, so notice what I'm doing. I'm just rewriting the answer from part B, but now I have decimals. So now I can say, okay, could it equal that? Well, let's see. The Lagrange error bound says it has to be between there. Is that number in that interval? Is it? No. You just compare decimals and you'd be like, no. So now we answered a complete question. F of 3 could not be 1.768, comma, because or since what? F of 3. Yes, you could. Here's what you could do. If you want to call this interval, what's a good word for an interval? If you put an I, make sure you put the serifs on it, the two horizontal bars. I for interval. That looks different than just like a 1 or something. But I'm going to use my name. I like capital K. Call the interval K because F of 3. Here's the simplest way to do it: is not in K. You can do it like that. The epsilon means is an element of, is inside of, and if you draw a line through it like that diagonally from top right to bottom left, it means is not in. Okay. Now, if you didn't want to call it K, I would just rewrite the interval again, since F of 3 is not in, and then just rewrite that interval. But that would be the reasoning, right? So it's a simple little task. Find the error, give an interval, and then compare some numbers. They might ask you for another one. Hey, part D, could F of 3 equal 1.761? And you're like, yeah, it certainly can. I don't know if it is, but it's a possibility. So now you could say, I would say this. Yes, right? Interjection for excitement or emotion. They're usually set apart from sentence by an exclamation point or by a comma when the feeling's not as strong. But you know what? My feeling is strong. Exclamation. Yes. F of 3 can indeed. Oh, look at that. Indeed be 1.761 because 1.761 is in the interval, is in K. There you go. Yeah, back up here, I said F of 3 is not in K. You would not lose points for that, but what would be a better thing to say there? Yeah, I'm going to come back and put the number there. There you go. That's better. I like that better. Because by referring to it as F is 3, I'm almost using an equality right there, right? Saying that it is that. Y'all might have sensed that and been like,
I changed it on mine.
oh, good. Thank you. Hey, speak up.
I should have.
Speak up. Yeah. I have all kinds of things on my brain. I'm trying to teach and energize and excite and make jokes and make not jokes and think about what I want to do next and today's pep rally all at the same time. Okay. Everyone's invited. Everyone's invited. Parents as well. Parents as well. Okay. So how was that? How was that for Lagrange error bound? Palatable, right? Yes. Yes, supremely palatable. All right, good. Fun. Okay. How much time do we have? What time we get out of here? Let's see. 12:34. Yeah, let's try one more. Let's try one more. Example 2. Calculator permitted. Y'all got one? Let's return to our original quandary, approximating sine of 1 with the idea of how accurate it's going to be. Find the 5th degree Maclaurin polynomial for sine of x. Then use your polynomial to approximate sine of 1 and use Taylor's theorem to find the maximum error. Hey, that's the same as what? Lagrange error bound for your approximation. And then give 5 decimal places. So notice they're trumping the 3, which is the standard. Okay, so do I need to reinvent the wheel and use Taylor's machinery to generate the Maclaurin polynomial for sine of x? No, but they didn't tell me where I'm supposed to center my approximation. Pooper scooper. 0. Yeah, they did. It's right there. It's Maclaurin, right? Remember him? He has a round face, looks like a 0 when you include his hair. The center's at 0. Okay, so the center is 0. And then the A value is 1. I'm just going to go ahead and get that out of the way because we're trying to approximate sine of 1. So I got my center and I got my value of A. Now, let's go ahead and write it out. Sine of x then, if you want to call it f of x, you can too. It's going to be approximated by, not equal, right? Why are we doing approximation and not equal? Good. It's a polynomial. Polynomials get squiggles. Series get equals. Got it? And that's a point that you'll lose a point on. That is a point of contention that could cost you. Okay. So what's the first term in sine? X. And then let's alternate, right? Minus x cubed over 3 factorial plus x to the 5th over 5 factorial. Can't stop, won't stop. Time to make the Taylor polynomial drop. Oh, well, yeah. I did 5th again. See, I can't even think of how to change the lyrics without messing up. How many terms is that? It's 4 terms. Did it say to write 4 terms? No, it said a 5th degree polynomial. What did I write? 7. You know, I was on my way to writing 5 terms. That would not be good, right? So remember, when you have polynomials, we usually refer to it by the degree, unless we have like the sigma notation, and then we could say for n equals whatever. So I'm going to back it off here, right? Back it up, get rid of that term. There it is, boom. Okay. Now, use it to approximate sine of 1. So just like we do with linearization, we're going to say sine of 1 or f of 1, if you want to do that, either way, is approximated by. Now, notice I didn't give a name to my polynomial. Do we need to? No, but if you want to, you can now say it equals m sub 5 of x, m for Maclaurin. You could also call it capital T sub 5 of x for Texas or Taylor, right? Right? Or you could just, you can't call it f of x. But at this point, maybe we don't even have to use that notation. I could just say sine of 1 is approximately, and then I plug in directly 1 minus 1 cubed over 3 factorial plus 1 over, or 1 to the 5th over 5 factorial. Now, that would be a numeric answer, but it says a calculator, and it said to give 5 decimals. So let's go ahead and type this in, someone who's willing. Now we use an equal sign, or I can work straight down with an equal sign. You don't need to put 1 cubed, do you? It should be 1 minus, you can almost do it in your head. 5 times 4 is 20 times 3 is 60. And 2 is 120. So 1 minus 1 over 6 plus 1 over 120. I'm typing it in. I'm not showing it on the screen here on the recording, but you have the buttons in front of you, right? The factorial button is under math, probability, number 4. All right, as soon as someone gets it, call it. 0.84. 166, 1, 2, 3, 4, 5 decimals. Good. Oh, good thing they didn't say 6 decimals, because we were about to get the devil in here. I mean, 666. That would have been an ominous answer. I'd been like raising my hand. I have to leave the test now, sir. I'm spooked. I heard someone walking around in high heels, clickety click, 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 and now Satan and Beelzebub are manifesting in my problems. Get me out of here. All right. It's my brother's birthday, though. Okay. Okay, we'll write it up there. All right, here we go. We're not done. It says to find the maximum error. So here we go. We're going to say then that the error r sub 5 at what? What value did we approximate it at? At 1? Is going to be less than or equal to the absolute value of, well, what number? Now, here's where we go back to n. When we look at the next unused derivative, we don't look at, you know, these are odd powers, 1, 3, 5. We don't go to 7, okay? We don't go to 7. We go to the next number for the derivative. Okay, so we don't follow this sequence here. We go to the next number, 6, right? 6. So it's going to be the maximum value of the 6th derivative at some z value all over 6 factorial times x minus c to the 6th. Now, I like to write that in parentheses, x minus c. I'm going to write that up there as a reference. What's our x value? It's really our a value, right? It's 1 minus, and our center is 0, okay? Now, here's the deal. I need to figure out what the maximum value of this function is on the interval. What? I need the max of the 6th derivative on what interval? 0 to 1. Good. From C to A or A to C. It doesn't matter, right? But that has to be in order from 0 to 1. Okay. Well, did they give it to me like they did in the previous problem? The maximum value of the 6th derivative is 7. They did not. Did they give me a graph that I can look at? No. Crap. how can I figure out the maximum pi and 6 derivative of sine? Can we figure out what? No, here we actually have to do the work ourselves. We could do it, right? F is sine of x. That's what we're doing. So look, the first derivative is cosine of x. Oh, that's easy. The second derivative is sine of x. Wow, there's a pattern here. I see it. The third derivative is, it's negative sine. Sorry, negative sine. Yeah. And then we get negative cosine. And then the fourth derivative, back to Arabic now, is positive sine. These repeat in cycles of 4, if you didn't know that. And now the fifth derivative, this is so much fun, is cosine. And then the sixth derivative, well, we get there pretty quickly, is negative sine. Okay. Now, here's the deal. Do we know what the graph of negative sine looks like?
Yes.
Yeah, the negative reflects it across the x-axis. So instead of sahala, it's salaha. Okay. But here is 1, here is negative 1, and we're on the interval from 0 to 1. 1 falls right short of the maximum value. Remember, it's the absolute value. What do I use for my maximum error? It would be whatever this value is at 1. It's whatever sine of 1 is, but I don't know what sine of 1 is. That's what I'm trying to approximate. Where's the closest number that I can get to that I know is safely going to include it? Well, we're looking at the y value. We don't even care about the x value. Yeah, negative 1. Let's use negative 1. But we're taking the absolute value of it, so 1. There you go. There you go. So this is what we're going to do. We're going to now replace this with an equal sign, and we're going to say that's 1 over 6 factorial times 1 to the 6, which is 1 over 6 factorial. And we could drop the absolute values once we make the 1 positive. So there it is. That's the maximum error. And you see that makes sense now because I don't know what sine of 1 is or negative sine of 1 is, but I know that if I go to 1, it's going to be somewhere within there. I can go to 2 as well, but that's losing accuracy. So anyway, that's it. I do want to work another problem. We won't finish this today, but Monday we will, okay? So there is a take-home test, right? And it's only 1 free response question now, and then 10 multiple choice. And we'll grade that on, did I say Tuesday?
When did it change from 1?
We did the other one in class. I did the polar one in class. Yeah. Y'all can go to lunch. Yeah. All right. So we'll make it do Tuesday. Yeah. The take home test, which is BC Review 12. Yes. BC Review 12, 10 multiple choice, and then the first free response. I'm going to make it due on Tuesday. Okay. We'll make it due on Tuesday. All right. Y'all have a great lunch. Oh, no after school.